Hello everyone, and thank you for joining this session about unlocking the artificial intelligence black box. Before we start, I would like to highlight a very important comment that automation is not intelligence. Automation had been there since a very long time, probably since the Industrial Revolution, and it's about repeating a series of steps over and over and over without any changing or adjustment to the surrounding circumstances. So automation is just doing the same thing accurately again and again and again without thinking, without changing. Before speaking about artificial intelligence, let's first speak about natural intelligence. Defining natural intelligence can range from very simple and intuitive definitions to very complicated, sophisticated, maybe scientifically profound definitions. However, in this lecture, we're going to use a very simple and intuitive definition, which is the ability to acquire and apply knowledge and skills. Applying the knowledge and skills to solve existing problems or to identify new problems or challenges when they arise, or even a higher level of intelligence is setting the new goals for the future or thinking, imagining, dreaming about a new future reality that's not there yet and working on conceptualizing these ideas until transforming them into reality. Looking at the human brain or the human nervous system where all the action of intelligence and thinking takes place, the building block of the human nervous system is called the neuron. Neuron is simply a nervous cell consisting of a cell body, which you see on the top, and then the axon, which looks like the tail of the cell, which is directly connected to the body. As you see, to the cell body, there are some branches connected to the body, and these branches are called dendrites. The branches are responsible for picking up the nervous signal from surrounding cells, and then the signals are summed up here in the cell body and then moves along the cell axon until reaches the end of the cell axon to go out from the cell on the other dendrites at the end of the nervous cell. The nervous signal flowing through the body along the axon till reaching the exit dendrites, this is the nervous signal, and it's in the form of electric impulse. The electric impulse representing a nervous signal is called action potential. When one neuron is already having an action potential, we call it ascending neuron, and this sending neuron is having the action potential traveling through its own axon until reaching its dendrites. Then the dendrites of the sending neuron is coming close to the dendrites of the receiving neuron. However, they're not touching. The proximity area of both dendrites from sending and the receiving neuron is called the synapse. Synapse is where the signal coming from the sending neuron reaches its dendrites, and through this tiny gap between the two dendrites, the action potential should be transmitted from the sending neuron to the receiving neuron and then starting a new action potential in the new neuron. So synapses are the way action potential are transmitted from one neuron to another neuron, and it's the way to harmonize the work of our whole nervous system, which includes more than 100 billion neurons that cannot work individually and need to be harmonized through quadrillions of synapses. To illustrate how things are working at both sides of the synapse and inside the synaptic gap, for example here, the upper neuron is having an action potential which travels through its axon until reaching the synapse. Now the higher neuron starts to release chemicals. When it reaches the lower neuron, the action potential is induced inside the lower neuron and it travels through the lower neuron's axon. The connectivity of the synapse is determined based on the amount of available chemical transmitter substances in the synaptic gap. So it's up to the synapse whether the signal will be transmitted from the sending to receiving neuron, or if there are no chemical transmitters, the signal will not be transmitted and it will stop at this synapse. Or if there is a limited number of chemical transmitters, only part of the signal will be transmitted through the synapse. Looking at the whole view now, everything happens inside our brains. Every idea that crosses your mind, every word you're saying, every word you're hearing, it translates into electric impulses flowing between neurons through synapses. So there is a lot of electrical activities going through our nervous system in forms of action potential through synapses. This is a very nice simplified visualization, and just to let you know the order of magnitude we're speaking about, this represents only 3% of our neurons and less than 0.0001% of the synapses in our nervous system. Looking at this simplified view of the neuron, it represents the neuron as a cell which adds up different inputs from neighboring neurons, but with different weights. So it's up to this synapse to determine how much of the signal coming through this neuron will be transmitted to the receiving neuron. The synaptic connectivity could range from 0, which means no signal will be transmitted, to 100%, which means the whole signal will be transmitted, or anything in between, like 50% of the signal to be transmitted, or 70%, or whatever. Then the receiving neuron cell adds up all of the weighted summation of all the signals, and if this sum exceeds certain threshold, action potential is induced and passes through the axon of the receiving neuron. If the summated signal cannot exceed the threshold, then there is no action potential and the signal stops there. For mathematics lovers, the neuron can be having a mathematical model representation as a sum function that gets a number of inputs, multiply each input by a weight, which is the synaptic connectivity related to this input, and then sums all of the weighted inputs together, compare it to a threshold. If the sum is higher than the threshold, the signal goes on, the action potential passes. If the sum is lower than the threshold, then there is no action potential passes through this neuron. So this could be a mathematical representation of the neuron. Summarizing the discussion about natural intelligence is getting down to synapse. Synapse is the way that's synchronizing the activity of all the neurons in the natural intelligence system in our nervous system. Synapses store all the information we know, everything we learn, everything we have in our memories as connection between neurons to harmonize the way we think or the way we act. Storing information in synapses is just in the form of synapses connectivity. So the selective connectivity level of each synapse, this is everything we know and everything we can think about. Hypothetically, if all of the synapses are erased from any nervous system, then this nervous system will stop functioning and will stop being intelligent. No cognition, no recognition, no memories, nothing. So synapses are the maestro of the nervous functions. Now we're moving from natural intelligence to artificial intelligence. Speaking about the evolution of the artificial intelligence takes us back to the 1950s. It was the early years of the childhood of artificial intelligence. During these years, artificial intelligence referred to some software programs that were written explicitly to tell the computers what to do in each and every anticipated situation. In these days, computers were not thinking or not trying to mimic the natural intelligence. Computers were just following a hard-coded software that instructs the system or the computer what to do in response to every set of input data. This can be thought of a dumb person who is not thinking but having a very intelligent mentor who tell him what to do in each and every situation. So this was referred to as artificial intelligence. However, it was not intelligence. Afterwards, at the 80s, a new concept started to evolve, which is machine learning. Machine learning is based on what's called artificial neural networks. And this, in my opinion, is the start of the real evolution of the artificial intelligence, because this was the point in time where artificial intelligence scientists thought to have the mathematical model of the neuron, you've seen a couple of slides before, as simply selective summation of the inputs through synapses, and put this as a mathematical model inside the computer to model an artificial neuron. Then, if you can connect a number of neurons together as a software, you got yourself an artificial neural network. Moving from the machine learning to deep learning is not something magnificent, is not something really different, but deep learning refers to artificial neural networks that includes many more layers than the conventional neural networks. So machine learning is about artificial neural networks, and deep learning can be thought of as a very large artificial neural networks, which is having many layers in between the input and output, hence the naming deep. Looking at the timeline to the left of this slide, you will see that the early childhood days of the artificial intelligence was very promising. It was the aspirations and the dreaming, the high hopes. But unfortunately, the computer's hardware, processors, memory couldn't keep up with the hopes of the artificial intelligence scientists. So between 70s and 90s, all of the great ideas of the artificial intelligence algorithm couldn't be implemented because the hardware was very slow. That's why this era is called the winters of the artificial intelligence, because it was a number of successive waves of high hopes and disappointments due to hardware. It was after the 2000, maybe 2010, where the hardware processing power increased exponentially and allowed for implementing all of the good ideas, the amazing ideas about artificial intelligence on a capable hardware. So the results started to take place in reality. This is a very simplified view of artificial neural network, where the mathematical model we've shown before for the natural neuron and neuron connections is just mapped in a software by artificial neural networks. Each of these nodes represent a neuron, and the arrows between these different nodes represent the synapse between one neuron and another. So this is a very simple artificial neural networks where you have input neurons that receive stimulus, hidden layer that do the processing and the thinking, and then the output layer that produces the outcome or the decision. Moving from a simple neural network with only one neuron layer in between the input and the output, and adding multiple intermediate or hidden layers between the input and the output makes the network more deep, and the depth is in terms of the intermediate layers, hence the name deep neural networks, and the learning for these networks is called deep learning networks or deep learning algorithms. As we already discussed during natural intelligence, all the information we know, all the learning we had is stored in the form of synapses connectivity. Copying the same idea to artificial neural networks, so connections between different neurons is forming artificial synapse. Teaching the neural networks is all about setting the selective connectivity of all of these artificial synapse to make decision of what neurons should fire in response to other neurons, or how the signal will move from the input to the output layer through different neurons in between. Teaching or training an artificial neural network is exactly done like teaching a young child about the world. So for example, here you input a photo to the system in terms of pixels here, and then you ask the system to produce an output which is one of the two choices, whether this is a cat or a dog. So if the input is a cat photo and then the decision that it's a dog, then the teacher tells the artificial system, no, this is a cat. When the system takes the information that this is a cat, it goes through what's called backpropagation process by adjusting all of these weights of the synapses, the artificial synapses, so that the output would be a cat. And then you input the photo of the dog and ask the system what's the output. The system tells you it's a cat, and you say no, it's a dog. So it gets back again through backpropagation to adjust all of the weights through different layers. You do this for so many times until when you put a cat image, the output is a cat. When you put a dog image, the output is a dog. You continue doing this for so many examples and so many photos until the system is well trained. So the neural network's training or learning is simply a matter of repetition. It's giving inputs and then waiting for the output from the system. The neural networks, the artificial neural networks, tells you the output. If it's correct, then say yes, nothing done to the weights of the synapses. If the output is wrong, you say no, and then the system goes through backpropagation to adjust all of the connections between different synapses. You keep repeating this through a large number of examples until the network is trained. This is an example of an artificial neural network which is trying to learn how to identify handwritten numbers. So first, the photo of the handwritten number is digitized into a number of pixels. These pixels are now fed into the neural network. The neural network keeps running. With each input, it produces some output. If the output is right, weights don't change. If the output is wrong, then backpropagation goes and adjusts the weights backwards. This process is repeated so many times until the network is well trained and able to provide the correct output corresponding to each input image. The previous discussion highlighted one type of learning, which is called supervised learning. By supervised learning, there is a trainer or supervisor who tells the system whether the output is correct or wrong, and then the system adjusts the weights of the synapses, the artificial synapses, accordingly. Another way of learning is unsupervised learning for the artificial neural networks, and this can only be done if the end result or the goal can be explicitly set to the artificial neural networks to optimize. For example, an artificial neural networks learning stock trading would have the final profit as a target to maximize. So with each and every trading transaction, the neural networks looks at the current profit. If it's going up, then the weights are going in the same direction. If the profit is going down, then the network has to adjust the weights and readjust the synapses of the new artificial neural networks. Now, with all of this background about AI, what the AI could really achieve so far, a lot of things can be achieved with artificial intelligence, ranging from recommendation of what you see on Netflix according to the previous movies you've seen. Then the system tries to identify the type of movies you like, to search engines, Google, Facebook, Amazon, trying to get you the results that you would like or similar to what you're looking for. Natural language processing, which means having service agents that can identify your questions, understand what you're saying, and then generate an answer to reply to you as if it's a human you are speaking to. And most recently is the advanced computer vision and self-driving cars. Looking at the core of what the artificial intelligence could achieve so far in different disciplines, you can simply position the achievements of AI under four tasks. The first task is the ability to break down or parse the input data into smaller elements. Secondly, is being able to identify each of these smaller elements or to detect the objects. Third is to understand what are the meanings of these objects, what are the relationship between these objects, and finally take a decision. There are a number of areas that artificial intelligence scientists and professionals are working on right now to trying to implement in the near future. Among these features are adding reasoning to the artificial neural networks, and also having multi-domain or open domain learning and conversations within the neural networks. So instead of having the neural network specialized in one domain or confined to only one domain, is adding the ability of the neural networks to generate knowledge combined from different domains, not just being specialized in vision or natural language processing or recommendations or something like this. Hot topics include applications in medical, self-driving vehicles, adding more functionality to robotics. A long shot would be adding ethics to the artificial intelligence algorithms. But more surprisingly, a new development recently happened in the area of the artificial neural networks is, instead of understanding objects from the real world, now generative adversarial networks, or GAN, are able to generate new content that never existed before. Like, for example, this photo of the nice lady. This lady never exists. It's a generated photo by an artificial neural network. Final section of this session is about the differences between artificial and human intelligence. Looking at the artificial intelligence, as we spoke, it's mostly related to the cognitive capabilities of the artificial neural networks. It has to be explicit, the target has to be explicit, or the role of the network has to be explicit, whether it's a vision or self-driving cars or conversational agents for the natural language processing recommendation system at Netflix, at Facebook. It's focused on one area and goal or task oriented. It's missing the consciousness of the human intelligence and the natural intelligence, that the system should be self-conscious and conscious about the context. This is not there on the artificial intelligence, and it's not anticipated to be there, at least in the near future. The emotional part is missing from the artificial intelligence system. The multidisciplinarity or the multi-dimensions and the multi-domains is not there. And much more importantly is the human intelligence includes so many implicit parts, so many implicit pieces of information. This cannot be transmitted to artificial intelligence. And that's why the fiction about having a competing artificial system to take place of the human intelligence system, this is not going to happen, because many parts implicitly embedded in the human intelligence, including consciousness, including emotions and everything, it's not there in the artificial intelligence system. Where the artificial intelligence system cannot mimic the natural intelligence, when you cannot explicitly describe the goal or the task in an explicit, detailed way, it means that you cannot tell what's the objective of the artificial network, and the artificial network cannot operate. Aspiring for a new future, a new reality, imagining a future that's not there before from scratch, this cannot happen with artificial intelligence. It takes the human intelligence to do this. Consider a problem which is having multi-facets coming from multi-dimensions, from multi-domains. This cannot happen with artificial intelligence networks, at least for now. And finally, the ongoing debate, and I think this will be going for a very long time, about the ethical and legal responsibilities. You cannot have the legal or ethical responsibility assigned to an AI system. An artificial intelligence computer system or a robot cannot assume legal responsibility. It has to be attributed to a human being, at least for the ethical and legal part, for the near future at least. Finally, if you look at the major difference between the human and the artificial intelligence, is the learning efficiency. Look at this baby taking the moves and look at this robot taking the moves. The human can learn from very few examples, and then human nervous system can do the corrections, can do the learning very fast with a limited number of examples. Robots, to do the same, they needs thousands, hundreds of thousands, or even millions of examples to learn the same thing as human. This is something which is having substantial effect on the differences between human and artificial intelligence, and this is the main differentiator now for the near future, and maybe for the far future also, that artificial systems will not be able to achieve the efficiency of learning achieved by the human intelligence system. So thank you very much for attending the session, and you're welcome anytime with the question at the end of the session. Thank you.